Welcome to our lesson on statistical evaluation. In our scientifically backed career, we make decisions that affect health, safety, and lives. And those decisions must be rooted in evidence, not just opinion or intuition. The quality of the evidence we use depends heavily on how the study was designed in the first place. And there are two main categories of research design: observational and experimental. Observational studies are when the researcher doesn't intervene at all. They just observe and record what's happening. On the flip side, experimental studies are more like running a clinical trial. Here, the researcher assigns an intervention and watches what happens as a result. These studies are more useful for answering questions about cause and effect, but they're also more expensive, harder to conduct, and come with serious ethical responsibilities. In this lesson, we're going to explore both, learn to identify different types of study designs, and start thinking critically about what kind of evidence each one can provide. Now, let's get oriented, because there's 9 types of study designs you need to be able to recognize and evaluate on the RD exam. Some of these are strong for certain questions, like what's happening in a population right now, while others are best for determining whether a treatment or a diet actually caused an outcome. So we're going to go one by one, starting with the observational designs. These are often easier to run, less expensive, and sometimes the only ethical option. But remember, they have real limitations when it comes to proving cause and effect. So if the researcher doesn't intervene, the study is observational in nature. These studies don't assign diets or medications. They simply observe what is already happening and record the data. Let's begin with descriptive studies. These are your most basic types. They describe characteristics in a population, often using survey data or health records. Descriptive studies can help identify patterns, like how many people are getting enough iron, but they can't tell us why. That's their biggest limitation. No causality in descriptive studies. Just because 2 variables are linked in a population does not mean that one causes another. Now, a case study takes a much smaller view into just one single subject or a small group. It tells a detailed story, maybe of a rare condition or a unique nutritional response. These are useful for hypothesis generation, but since there's no comparison group, we can't generalize here. Ecological studies look at data at the group level, not the individual. For example, you might compare average fat intake and heart disease rates across countries. This can be useful for spotting patterns, but it's risky. What's true at the population level may not hold for individuals. That's called the ecological fallacy, and we see it all the time in nutrition research. Cross-sectional studies are like a snapshot in time. They're great for estimating how common something is, like how many people have low vitamin D. But since everything is measured at once, we can't say what came first. Is vitamin D causing poor health, or do people with poor health just spend less time in the sun? It's a chicken and egg problem, and cross-sectional studies cannot get around it. Case control studies are retrospective, meaning they look backwards. They start with people who already have a condition, like type 2 diabetes, and ask, what did these people do differently from those who don't have it? These studies are great for studying rare conditions because you don't have to wait around for new cases to appear. You already have your cases. But the catch is you're relying on people's memory. Try remembering exactly what you ate last Tuesday, let alone 5 years ago. These studies are greatly impacted by recall bias, and it can seriously distort results. Still, when done carefully, case control studies can provide important insights. And finally, cohort studies. These are prospective, meaning they follow people forward through time. You start with a healthy group, measure a bunch of variables like diet, lifestyle, biomarkers, and see who develops conditions down the road. The famous Framingham Heart Study is a cohort study that's still going on after 70 years. The strength here is timing. Because the data is collected before the outcome happens, we can make stronger inferences about cause. For example, if people who eat more fiber consistently have lower rates of colorectal cancer rates 10 years later, that's valuable information. But cohort studies are slow and expensive. They require massive participant commitment and funding, and people drop out, and variables change, and you may not see results for decades. So each of these designs plays an important role in nutrition research, especially when experiments aren't possible or ethical. Observational design helps us make the most of what's already happening in the world, though none of them confirm causality, and a lot of them have potential for confounding variables. The way we address these issues is with experimental designs. Experimental studies are the gold standard for testing cause and effect relationship. Unlike observational studies, they assign a specific intervention, like a specific diet, supplement, or feeding protocol, and then observe what happens. The ability to manipulate variables is what sets experimental designs apart and makes them so helpful for drawing conclusions. Let's begin with a quasi-experimental design. They bridge the gap between observational and experimental studies because they have an intervention, but they don't have full randomization. For example, participants might choose which group they want to be in, or they might be assigned based on convenience, like which clinic they attend. That means the groups might differ in important ways even before the intervention starts. Quasi-experiments are more vulnerable to selection bias, but they're often used in public health and clinical settings where full randomization isn't practical or ethical. These studies give us insight into how interventions work in real-world environments. Next are crossover trials. In a crossover trial, every participant receives both the intervention and the control, but at different times. Imagine a group of participants who all try a Mediterranean diet for 6 weeks, then return to their usual diet for a break, called a washout period, and then try a low-fat diet for 6 more weeks. Because each person serves as their own control, that makes it easier to detect true effects, even with a small sample size. But crossover trials take a long time to complete, and they only work when the intervention doesn't have a permanent or lingering effect. So you couldn't do this with something like weight loss surgery or a long-term medication. And then we have the randomized control trial, the RCT. This is the gold standard. In an RCT, participants are randomly assigned to a treatment group or a control group. This could mean getting a high-protein supplement or a placebo, following a new diabetic diet plan or the standard one. Randomization is literally in the name, and it ensures that any differences between the groups are due to the intervention itself and not other confounding variables. And often RCTs are blinded, meaning the participants and even the researchers don't know who is in which group, further reducing bias. So RCTs are the strongest design we have for establishing causality. They are the foundation of the evidence-based practice in nutrition and medicine. Most of the dietary guidelines you'll learn and eventually apply are rooted in findings from well-constructed randomized control trials. But they come with trade-offs because randomized control trials are expensive. They take time, and they don't always reflect the messy, unpredictable world. And for ethical or logistical reasons, we can't always randomize people to certain conditions. You can't just randomly assign someone to, say, smoke for 20 years just to test its effects. Still, when well-designed and well-executed, RCTs provide the clearest, most reliable answers to our clinical questions. Before we move on, let's bring it all together. You should now be able to identify the major types of study design: 6 observational, 3 experimental. Of all of these, RCTs provide the strongest evidence. They help us go from observing associations to establishing causation. But remember, each design has its place. It's not about memorizing a list. It's about knowing when to use and why. Now, in order to analyze scientific research, we need to understand the scientific method. You've definitely seen this before in science class, biology, or chemistry, and it starts with an observation. Maybe we notice a rise in childhood obesity or a change in food patterns. From there, we research the topic. We want to know what other researchers have already published on this same topic to help us build context and create our hypothesis. For example, if children eat more ultra-processed foods, then they will gain more weight. The hypothesis must be testable. We can't just ask, is junk food bad? We need a clear and measurable question. Then we design a study to test it. This includes deciding on our population, the intervention, the control group, and whether the study will be observational or experimental in nature. Once the data is collected, we move into the analysis phase. This is where we test our results against something called the null hypothesis. The null hypothesis is the default assumption that nothing has changed. There's no effect. And any difference we see are just due to random chance. Let's say we're testing a new high-protein supplement to improve muscle mass. The null hypothesis would say the supplement has no effect. People who take it will gain just as much muscle as those who don't. When we analyze the data, we're trying to see if there's a difference enough in the evidence to reject that idea. If the results show a statistically significant difference, meaning it's very unlikely that the outcome happened by chance, we may reject the null hypothesis. And that opens the door to accepting the intervention, like our protein supplement might have actually made a difference. So then finally, we can share out those findings. Not just what we hope to see, but what the evidence actually shows. Because good science is transparent, reproducible, and honest, even when the results aren't what we expected. It's important to remember that throughout the whole research design process, we also need to be mindful of the people involved. I'm sure you've heard of the Tuskegee syphilis study, a famously unethical study where Black men were denied treatment and lied to in the name of research. But have you heard about the Canadian First Nations nutrition experiments? In the 1940s and 50s, researchers in Canada ran experimental nutrition experiments on Indigenous children in residential schools. Researchers deliberately withheld vitamins and calories to study the effects of malnutrition. These children never gave consent. Their families weren't told. These children were not treated as people, but as data points. Many suffered. Some died. This is why we have the IRB, the Institutional Review Board. It exists to ensure that research involving people is ethical, informed, and respectful. The IRB reviews studies before they start. It checks for potential risks, ensures participants know what they're agreeing to, and demands that researchers minimize harm. In nutrition, we often work with vulnerable populations, like children, sick individuals, and low-income communities. That's why ethics matters so much. The core principles of research are respect for persons, beneficence, and justice. Respect means informed consent and voluntary participation. Beneficence means maximizing benefits and minimizing harm. And justice ensures fairness in who bears the risks and who receives the benefits. These ideas show up again in the Dietetics Code of Ethics, which we'll talk about later on in the course. The IRB evaluates whether a study meets those principles. Sometimes it approves a study right away. Sometimes it requires changes. And sometimes it rejects studies outright because the risks are too high or the design is unethical. We can't move nutrition science forward without trust, and we can't earn that trust without ethics at the foundation. And the IRB helps make sure we get both right. And with that, we've wrapped up part 1 of our lesson on statistical evaluation. Next, we'll get into how we analyze the data, interpret the numbers, and make sense of the evidence.